welcome to the NUPOC Study Guide Physics Review video. And my name is John Sinclair. This is my email address. If you have any questions as I go through this, if I happen to make a mistake, or if you have any comments or any questions, feel free to email me, and I'll get back to you as soon as I can and go over any of those questions that you may have. And my email is john.a.sinclair@chess.com. I use chess.com because I'm an amateur chess player. Maybe one day I'll be a grandmaster, but I like the email domain. Anyway, so if you have any questions, feel free to email me. Basically, what I'm going to do in this course is just review question by question the physics portion of the NUPOC study guide, and hopefully what this will do is give you a good review of all those physics problems. You can get exposed to it, see them work through it a little bit, and this hopefully will prepare you a little bit more for interviews at naval reactors. So without further ado, I'm going to begin and start with question 1 and work through, I think there's 26 questions here, so I'm going to work through each of those with you right now, and hopefully we'll gain a better understanding of those problems as we go along. So let's see, I've got my fun sponge here. Wipe that off here, and I'm going to get started right away. What I'm not going to do, I'm not going to write the questions on the board. Hopefully you have the NUPOC study guide with you right now. So I'm just going to read through the question with you out loud and kind of work through the problem that way. But just review, if you want to review to the question, just go to the study guide. Okay, so I'm going to start with question 1. The first question is, what must the angle theta be in order for the block of mass m to start sliding? So I'm going to go ahead and draw the diagram here. And as you can see, this is an inclined plane, and there's an angle theta, and there's a mass m that's on the inclined plane. They also tell you that mu, or the coefficient of sliding friction, is 0.8. So obviously that's going to be important with the problem here. So the main thing that you need to identify is that when is this going to start moving, or what angle is this going to start moving, and you kind of, depending on what the mass is, whatever angle it hits, it's going to start moving. So basically, we're going to solve for that angle using a couple physics equations, and kind of break down the vectors of the forces that are involved. So I'm going to go ahead and do that for you here right now. So number 1, basically what you want to do is break it into both its y vector and x vector component. So the sum of Fy, or the forces in the y direction, should equal 0. And that's, you get the normal force, the force that is coming from the inclined plane, minus the force due to gravity in the y direction, okay, is FGY, right there. Okay, so what's interesting here is what I want to show you is that gravity obviously points down here towards the Earth. But what this does is it forms a balance, because the normal force is always coming out of the object that's being kind of pushed on. So here we have the normal force coming out. Well, the y direction of the gravity force is here. Now there's what you can do is basically you take this angle here, this triangle, and you kind of flip it, and it goes here. So this angle here is actually theta. Okay, so the y component of the force is the adjacent side, and this force here, of course, is mass times gravity. So that's the amount there. So this is actually normal force minus the gravitational force times the cosine, since it's the adjacent side there, the cosine of theta. Okay, so we've got that. Next, we want to look at the forces in the x direction. Okay, and those, of course, are going to equal 0 to get balanced out, because anything greater than that is going to force this mass to move. So here we have F in the g direction, x minus F friction, okay, and that's going to be equal to 0. Okay, So there is a force coming this way and a force resisting, which is the force of friction. Okay. Fortunately, we have a coefficient of friction here, and we also know that the force is based on gravity pulling it down, which is mg going to be sine theta, because that's an opposite side. So this is equal to mg sine theta minus coefficient of friction times the normal force. And that basically, that's just something you need to know. Okay, so the coefficient of friction times the normal force is the force due to friction. Okay, so when you subtract those out, it needs to be 0, and basically they gave us the information there, so you kind of just need to solve. So here, this is equal to mg sine theta minus mu times mg cosine theta. All right? Because mg cosine theta we get here. Okay? Because that's basically what we're going to get for the normal force. Because they're equal, the two forces there. So, you can do some simple cancellations here. So the m's are going to go away, the g's are going to go away, and basically this is equal to sine theta minus, I forget, it's all equal to 0, minus mu cosine theta. And you basically know a couple things here. I'm just going to move this to the other side. So cosine theta, mu cosine theta, is equal to sine theta. Just move that over there. And then mu is equal to, if you divide out cosine, is equal to sine theta, all right, divided by cosine theta. What's that really mean in trigonometry? Sine theta over cosine theta is tangent theta, okay? So if mu is equal to sine theta over cosine theta, well, what's theta equal to? Okay? Well, if that's, sorry, it's equal to tangent theta. Well, it's going to be equal to the inverse tangent of mu. So you just need to do a calculation on that, and inverse tangent of mu is equal to theta, and that's going to be equal to, just plug it in, and I think it's in your book right there, it's some decimal, but you can always approximate. So that's the angle theta that you need to get that block moving. Okay? Great. Get my handy sponge out here. So that's the main thing here is you basically need to identify your forces so that you can solve for theta. All right, good deal. Next question. Find the final velocity of m for both elastic collision and inelastic collision. And they give you this diagram here. So we got a big mass here, m, with a velocity 0, which is coming towards this other mass, m, with its small velocity, 0. Okay? Elastic and inelastic collisions, you're going to need to know those. You're going to need to know conservation laws, conservation of energy, and you'll be able to combine those laws to figure this stuff out. So this one here, I would just real quick, I'm going to skip to the inelastic one. It's a little bit easier. If you assume that it's completely inelastic, you don't have to worry about conservation of energy because energy in an inelastic collision is gonna go somewhere else too. There's gonna be energy that goes to heat and other various types of things, mostly heat. In this case, though, for inelastic, you basically just use your momentum. So your conservation of momentum is mv0. Right now, in an inelastic collision, they're going to combine and move forward. So that combination is going to create heat and other energy that's going to be dissipated elsewhere. So you can't use the energy